So we have seen a very overall difference between convex and non-convex function. Now let's see how we can convert from non-convex to convex. So it's a bit trick that we have. So just ignore this particular this particular uh, diagram right now. It's not there is a mistake here. Anyway, it will come later. So assume a situation like this. So we have a cost function like this, right? Cost function like this, where just for simplicity, just to keep the equation simple, I am assuming yi cap minus yi as cost of yi comma yi cap comma yi. Okay, so this cost comma this is representing this part, cost function. Okay, where yi cap is 1 by 1 plus e to the power wtx plus d. We all know that already. We have seen this is a sigmoid function. Now one thing we can do here is that we can actually redefine the cost function in a different way. What is the difference is that we all know that cost function is nothing but the difference between the predicted output and actual output. We have this actual output in our data set, and this predicted output is we are finding based on applying sigmoid function over wtx plus b. So, and as a result, if we try to find a derivative of this, you will see that as a result, it's a non-convex function. So if you try to apply directly gradient descent on this mathematically, it's not possible to reach to global optima. That already you have seen. That is why what we are doing, we are trying to redefine the cost function such a way that we are trying to force this cost function, the difference between these two, to be considered as either minus log of y cap I or minus log of 1 minus y cap I. Minus log of y cap I we will consider if the actual output, if I see, it's 1. And if I see actual output is 0, then the cost function of this yi cap and yi considered as minus log of 1 minus yi cap. So naturally a question will come in your mind that why exactly we are taking these two different scenario. Why log of y cap I? Something like minus log of this, right? So you see, it's very difficult to show you mathematically right now because of foundation of time, but you can in your home you can actually try to check a graph between yi cap and minus log of yi cap. I mean, actually yi is not varying. Yi is a fixed value that I have in my data set, but this yi cap will vary based on how good my the straight line is, right? How good this wtx b is. Based on that, this yi cap will vary because this is the predicted one. Now that mean if we try to check the how this minus log of yi cap is varying with respect to changing value of yi cap, that is presented over here, you'll see my yi cap versus minus log of yi, you will be the graph will be something like this. So when yi is towards it's increasing, minus log of yi will decrease. Okay, you will see that. You can see that you can simply check in your calculator as well. Okay, this is one side. Now the another side is when yi is equal to 0. I mean this side, right? So it's like for the, and if you see what happened for minus log of 1 minus yi cap, you will see it's basically increasing. Something like this. It's exponentially increasing for with respect to yi. So if yi increases, this particular curve, the value of minus log of 1 minus yi will keep on increasing and look something like this. Okay. So what you can do, why I'm taking this two, just if you think that we have two different curve here, okay, for two different scenario, y equal to 1 and y equal to 0, what will happen if we merge these two? If we merge these two, it will be something like this, right? And you see here, this particular things becomes a very smooth convex functions like that what we have in linear regression, right? So as a result, I can get, if I somehow merge this, I can get, a curve like this. So now merging means what? Merging mean we can simply write the cost function in this way. You see, don't get confused. The cost function yi cap comma yi is basically written in a different way. The same thing, because you see what I have written here, minus yi multiplied by log of yi cap plus 1 minus yi multiplied by log of 1 minus yi cap. What does it mean? It means that, you see, it's nothing but uh, it's nothing but okay, sorry, I have a mistake actually here. It's plus then minus log will be there. Okay, plus minus log, I mean this whole thing. So I'm just adding these two multiplied by this. So what benefit we will get? You see, when yi is equal to 1, then this should be activated. I mean this line should be used, not this line. So you see, when yi will be equal to 1, this 1 minus yi will be equal to 0. So this entire term vanishes. So cost function become this, because yi is mean 1, that means minus 1 into log of yi cap, which is this one, if yi equal to 1. Now when yi equal to 0, then naturally this term now will be vanishes and this term will be left, and it will be 1 minus 0, right? That means 1 into log of 1 minus yi cap, which is this one. Just I forgot to write minus here, jo just a typing mistake. So it's like the addition between these two multiplied by this. I mean this one multiplied by this plus this one multiplied by this. Okay. So the cost function that I have written in this equation and this equation is basically representing same. Okay, don't get confused. And what is the benefit of this? Just by adding this, I am getting a function, addition of these two function, and it looks like a convex function. So since it becomes a convex function, now we can apply gradient descent. So now the error that we have here will now look something like this. So what we have, this cost function over here, will be now modified by this cost function over here. I mean the error function like this. So, and remember, this is what we call maximum log likelihood function. Okay, so these now definitely, it's, I have not actually derived the error equation again by some derivation. You can do in your home if you want, but what my intention was to show you that what exactly reason for different creating of the error function, what is the issue that we can face if we have sigmoid function and something like this. Okay, so once you get this error naturally, just you can simply find the derivative with respect to the weight, and the derivative of that will be used for the gradient descent that already we have seen in our previous classes. Right. So we can stop the understanding a conceptual overview of the logistic regression function. I mean logistic regression algorithm rather. So what you can do now, we can actually try writing some code, corresponding Python code for this. Okay, and let's see what will happen.